So we have the function f at x is equal to 1 over 1 plus x squared. And you want to represent this in a power series, right? So how do we do that? Well, immediately there really isn't, I mean, I'm sure there is, but there isn't a clear way to represent this as a function unless you want to memorize sort of the general formula for something that always looks like this. I don't know, x squared. There's not really an apparent way to do it, but there's something about series that we can use to form this power series representation. So first, represent this using a negative exponent. Same thing, right? Now we're going to differentiate it. It'll become apparent why. So now once we differentiate this, we get 1 plus x to the negative 1, right? And this is the same as negative 2 over 1 plus x to the 1. Now once we've differentiated this, now you can see this is in a more manageable state, right? Yep, like we know how to do this. Because from here we can extract that our a value would be negative 2, and then our r value would be negative x, right? That's easy. So let's do that. So this would be infinite series from n equals 0, or really n equals 1 because it's the derivative. A negative 2 times negative x to the n equals 1 to the infinity, negative 1 to the n, x to the n. Here's another thing you can do actually. Basically, since we have negative 2 here, we can break this down to negative 1 times 2. So you get n to the 1 to the infinity, negative 1, n plus 1 times 2 xn. Cool. This is the most simplified way we can show it. Now, we know that the relationship between f prime at x and f at x is that the integral of f at x, f prime at x is f at x, right? So let's do that here. Let me do a different color. Right? So for us to maintain this equality, that f prime at x is equal to f at x, we just do this. Right? So all we have to do to describe this original function, f at x, is integrate the series representation of the derivative of it. Right? So let's do that. We can take out the summation symbol, n equals, we'll say 0, because once we integrate it, we'll get the original c0 term, right? You can take out the negative 1 to the n plus 1, and the 2 is a constant as well, so 2, and then you have the integral of x to the n, we'll say dx, of course, not to keep it an integral, correct? Now you know the general formula to an nth power integral. That's pretty easy. So now if we were to express this, we would have the sum from n equals 0 to infinity, 2 times negative 1 n plus 1, and then this will all be over n plus 1 times x to the n plus 1. Cool. Yeah. You might want to combine those powers, but I don't think you should. Usually you like to keep that alternating term separate. Again, you can do whatever you like. But as a note that you should make here is where this summation starts and why it changes. So here, if we had described f at x as a sum, it would be in the form red and blue, c0 plus c1x plus c2x squared, and dot dot dot, right? But of course, if we were to differentiate this, so d over dx of this entire thing, this term would become 0, right? So this becomes 0 plus c1 plus c, or 2 c2x plus dot dot dot, right? So you can automatically see here that since this first term has no x, and this first term really doesn't exist either, like the 0th term, I guess you could say, your summation should start at one term later. And that's kind of where it goes from. So again, extending to that, if you were to take f double prime at x, this would be infinite sum from n equals 2 to infinity and whatever happens. So that's just a special note. I think during a test, if you were to forget that, unless you have like a really observant TA, they won't care. But a special note to make. Other times you check the initial Number is when you're looking for asymptotes or something. That's special cases, but you'll see why. Cool. Hopefully that helps. Okay, now they also asked for the radius of convergence for this one. As you should know, when you take the derivative or the integral of any function, the radius of convergence stays the same. Okay. But since we have this function, we can take the radius of convergence anyways. Or find it at least. So let's do that. Now here we have the absolute value. Of course, we're taking the limit as n approaches infinity of 2 times -1 n plus 2 x to the n plus 2 over n plus 2 times n plus 1 over 2 times -1 to the n plus 1 times x to the n plus 1. Okay, now what disappears? Of course, immediately the 2's. These always disappear because of the absolute value. These remain, and of course, the n terms disappear. Now you get left with, the limit as n approaches infinity, absolute value of, we'd have x to the 2 over x to the 1. We're going to simplify that to x, right? Because you notice here, x to the 2, x to the 1. And then you have the ratio of n plus 1 over n plus 2, right? And you already know how this works. If you have the same power on the top and bottom, it is the ratio of the coefficients, a over b, that the function approaches as its variable approaches infinity. Now here our variable is n, and the coefficients are 1, 1, and x, right? So of course this approaches absolute value of x, and of course we force it to converge, right? So it has to be less than 1, less the radius of convergence is equal to 1. Because we can extrapolate that x must be between, right? So like a number line, if you went like this would be negative infinity, infinity, 1. So it sort of exists here, right? Now, use part A to find the power series of this. So we have here x plus, 1 plus x to the 3. Right. How do you do this? Okay, well, you have, again, it's asking us, well, it's telling us to use part A. So we'll do what we did in part A and then see what we can do with that. We'll take the derivative. You get that it's -3 over 1 plus x squared. Okay. What can we do from here? Well, we can recognize that this is equal to -3 times, how can I do this? Okay. Let's keep this as f of x, right? Now I'm going to rename this as g of x. Okay. Now we can see here that this is -3 times g prime, no, literally g of x. Right, can you see that? You have, okay, I'm stupid, wait, sorry, f of x, that's what I meant to say. F of x. This is -3 times f of x, right? And since this is -3 times f of x, and we know the series representation of f of x is this, we can write this as -3 times, in brackets of course, we'll just copy this. Alright, cool, there you go. This will be that, -3 times this, because constants can get out of the series, we have this. Which means that all we have to do is recognize one more time that g prime at x and g at x are related by one integral. So all we have to do is integrate this, right? And you can do that once more. So let's do that. Here we'll take out the constants. We have -6 times -1 to the n plus 1. Interesting enough, we can do this now. Do that out. Okay. Now you have all of this over n plus 1. times, of course, the integral of x of n plus 1 dx. We'll put a dx here as well, just to reiterate that it's the derivative. Okay, now you also know the integral of this. This would be 6 negative 1 n plus 2 over n plus 1, and now we have a new coefficient of n plus 2, right, times x of n plus 2. All right, and of course this is the series now, and this also starts at 0, n equals 0 to infinity. Right, so this is what they mean by using part A as a tool for you to do this. And even if you hadn't seen that, you could instead just differentiate this again. You'd see g double prime at x is equal to 1 plus x, 1. Right, you can see that really clearly. And then you can do the same thing you did here. Let me actually demonstrate that's the same thing. Hopefully, if I didn't do anything wrong. We can extrapolate from here. A is equal to 6, r is equal to negative 1. So this gives us the series 2 because it's differential. Okay, cool. That makes sense. Now, all we have to do is integrate this twice. You'll have 6 x to the n dx. You'll have x to the n. Alright, now let me integrate this once more. That over n plus 1, n plus 2, x to the n plus 1. Alright, cool. Now, the issue comes in our variance here. So this exponent on the negative 1 to the n is different, right? And you can immediately recognize that. So, before you yell at me, we can actually see what that is. Again, going back to the fact that if you take the derivative, that first term, or the nth term, cancels out. And by n, I refer to the nth differential. So if I take the double derivative, these two terms cancel out, right? So I'll get left with this. I'll have a c2 as my first term, then I'll have 6 times x to the 3, something like that, sorry. c3, x to the 3, whatever, something like that. Right, so those two terms disappear, which is why you need to, again, this is when you have to pay attention to that sign. That's when you add the plus 2 here, right? So here I should have had a plus 1. Then you integrate again, you get plus 2. Right, so you get the same thing. 6 times that over that. Yeah, same thing. Okay. That's a cool question. Okay, let's try that. Now here it's asking us in part C to find this. So f at x, we'll call h at x actually, is equal to x squared over complex x cubed. Okay, so what do we do here? All right, we're gonna have to use another fact that we know about series, which is that first of all we can express this as x squared times 1 over 1 plus x cubed. Okay, now what do we have to recognize? We have to recognize that we have two functions here. Put some good names. Okay, we'll say a at x, and this is b at x. Okay, now of course together this is h at x. Okay, now the special property of series is that if you had the product of two summations, so like n equals 0 to infinity of a of n times the summation of n equals 0 to infinity of b of n, you'll get a new series, which we'll call c of n, but this c of n is defined as the product of a of n, b of n, right? So using this fact, we can extract two different series to represent x squared. So let's say a at x, n equals 0 to infinity, times our b at x, right? Okay, so how do we do that? Well, we already know the expression for b of x because we just found it right here. right? So this is our b at x. So how do we find a at x? Okay, we have x squared and you want to express it as a power series. How do we do that? So x squared can be represented as the general, or using the general formula, a of n minus c to the power of n, right? Where a of n is some coefficient, and then c is some, I guess we'll call it shift, and x is the variable, right? So here we can recognize that this is 1, say here 1 times x minus 0 squared, right? So that means x squared is equal to the sum 0 to infinity of 1 times x minus 0 to the n. But there's an issue with that. Why? Well, if we were to expand this out, x squared is equal to 0 plus 0 times x plus 1 times x squared plus 0x cubed plus dot dot dot, right? So what you recognize here is that the coefficient is 1 for only the x squared term, but everything else is 0. But to express that, I guess you'd have to just do n equals 2 to 2. I don't know. It's kind of a dumb way to do it, but I guess that's the only way to do it. Let's see here. How do we do this? Okay, well, using that fact, we'll just go off of that. That means we have to express this as the product of this series 2 to 2 of x to the n times n equals 0. Right. What you have to recognize, again, is that the x of n will be 0 for n equals 0 and n equals 1, right? Because literally here, you can see that this exponent begins at 2, right? So the terms x0 and x1 don't exist for a series expression of x squared, right? So using that fact, you can say that this we know, that's all correct. This we know, okay. Now we also know that this must start at 2, but of course you can go all the way up to infinity, just as this one does, right? But then you still have the issue of the non-matching bounds, right? How do you combat that? Well, you first say that since x of n, when n equals 0 or 1, results in 0, then basically the first two terms of this series also become 0, right? Because it's 0 times, we'll say this is, b of x, right? Plus 0 times b of x, right? So now we have the matching bounds. Because since these two are the same function, they're part of f at x, or what we call h at x, those two first terms must not exist because of the non-existence of this function here, right? So with that, you can say these two terms go away. Let's see here. So if we want to adjust the bounds, all right, so if you understood up until here, this all makes sense. Now for this, let me just say it one more time, just for clarity. Again, this x to the n is modeling, or attempting to model, the function x squared, right? But we know that when n is equal to 1, when the power is equal to 1, or 0, the entire term is 0, right? Because it's acting like a coefficient multiplying or scaling this other series, right? Which means that not only does this have to start at 2, but so does this, right? Because the 0th and the first term of this series would also have to disappear, right? Because this has to be 0. Now, knowing that, what do we do? Okay, since we'd have to disregard the first two terms of this series. We would have to subtract 2 from both of these powers, wherever n actually appears, actually. So basically you'd have, if you were to transform this, you would have 6 times -1 to the negative, or n minus 2 really, times x to the n, because it's 2 minus 2, over n minus 1 times n, right? And then this would still be x to the, x to the n. But now, since we have the two proper series and the same bounds, we can take the product of both, and they both have the same bounds, n equals 2 infinity. But because we made this adjustment of subtracting the powers, we can start this n at 0. Thus we get the final series of n equals 0 to infinity of 6 times -1 to the n minus 2 x of n, or 2n actually, over n times n minus 1. Yeah. Now hopefully this makes sense.